Pyrrole. This is one of the important topic, the first heterocyclic topic for third year. So normally who have seen our earlier video, we have described that benzene is an aromatic compound, right? And also cyclopentadiene cation, also an aromatic substance. Why? Because both of them follow Huckel 4n+2 rule. Whoever, if you want to know about this aromaticity, you can refer to our earlier video that these compounds are known as aromatic compounds. Okay. Now the moment you insert a heteroatom, that is oxygen, nitrogen or sulfur, inside this aromatic nucleus like this, okay, I'll insert one nitrogen over here, okay, and the moment you insert, it becomes heteroaromatic nucleus. Okay, that's the birth of the heteroaromaticity. So this is known as heteroaromatic compound. Similarly, I can introduce a nitrogen over here. Okay. Now, the difference of these two type of nitrogen is the lone pair of this heteroaromatic nucleus, which is known as pyridine, is not delocalized in the ring. Okay, it is not participating in the resonance. So that's why this lone pair is always available, and that's why pyridine can act as weak base. Okay, and on top of that, this nitrogen is sp2 type of structure, this nitrogen. But over here, to fulfill the heteroaromaticity, the Huckel 4n+2 rule, if you know this, Huckel 4n+2 rule, this has to participate in the resonance in order to fulfill the 6 electron concept. Okay, and that's why this structure is known as Pyrrole, which is heteroaromatic, but it is 5-member. Okay, so now after this, we should know the understanding of these two structure. If you see, the nitrogen over here is sp2 and over here is sp3. So this nitrogen always have a tendency to pull the electron towards itself. So I can just write a structure over here for pyridine. After pulling the electron, and one thing you must remember, the numbering always follow from the heteroatom. OSN, okay, 2, 3, 4, 5, 6. No matter, like if 2 position is amino group is present and 3 position carboxylic acid present. In normal IUPAC, carboxylic acid is more preferred, but over here it is not like that. It is as per the number. Like it will be 2 amino, 3 carboxy pyridine, or you can say 2 amino pyridine 3 carboxylic acid. Okay, in that case. So now, if you see, the electron density of nitrogen is increasing in this particular structure. So any nucleophile, it is very favorable position to attack the second position. I can just write second, third, fourth, fifth, because I have seen, I have shown over here the electron from this side. So first, second, third. So any nucleophile, the second position, fourth position and the sixth position is very favorable to attack. Because why? The nitrogen being an electronegative atom, it accommodates the electron on its. Okay. But if the electrophile comes over here and attack, what happens? This bond has to be given to the electrophile and the nitrogen become positive. So positive nitrogen is not a favorable condition. So that's why electrophilic addition won't be taking place in second, fourth and sixth. Now, altogether, if you see, the benzene is very good for electrophilic aromatic substitution. Those who have seen our video in EAS and NAS, please refer to that video. Why electrophilic aromatic substitution benzene give? Because the pi cloud is intact. Okay, See, in order to participate in the reaction, the pi electron has to be given to any electrophile which is coming towards the benzene. But the problem in the pyridine, the pi electron is reducing, pi density. Okay, why? Because the nitrogen is pulling the pi electron towards itself. So that's why for pyridine, the electrophilic aromatic substitution is very, very rare. It's required a vigorous condition. Okay, even though the third and the fifth position of pyridine is favorable for electrophilic substitution, but still it is not giving easily at all. Okay, because the ring current is reduced, pi electron density is getting reduced. Okay, but over here the pyrrole, it is not like that. Pyrrole, because nitrogen is giving the electron, so the electron density is maintained. Okay, so in that case pyrrole is very good for electrophilic substitution. Like you can, the second 1, 2, 3, 4, second and fifth position both are equal. So all both of the position pyrrole can undergo electrophilic aromatic substitution, like you can say nitration. Okay, nitration, or you can say, I can add MgX, that is your Grignard reagent. I can add lithium, okay, organolithium compound. So this is a fact that pyrrole can give very easily electrophilic aromatic substitution, but pyridine not. Pyridine can favorable for nucleophilic substitution. Now second position pyridine. Now you have a very famous reaction for pyridine, nucleophilic substitution reaction. That is, if you add sodamide, NaNH2. Okay, it is Chichi-Babin reaction. Chichi-Babin. The pyridine gives the second product, second 2-amino. Because the bond is this side, I will be writing the 2-amino pyridine very easily. It is the in case of nucleophilic substitution reaction. Similarly, if you add potassium cyanide, KCN, CN will be added in the second position or the sixth position. Okay, but when you add H2O2, the pyridine can form pyridine N oxide, and this change its reactivity. Pyridine N oxide direct nucleophile in exactly opposite position, that is the second 1 to 3rd position and the 5th position. Because why? Now over here the nitrogen is getting getting the electron. If nitrogen getting the electron from the oxygen, okay, so nitrogen won't be required for the it will not be pulling towards the nitrogen, this pi electron. So that's why the very important fact is that this sp2 nitrogen is no longer now sp2 nitrogen, because it is not pulling the electron towards itself, because oxygen is giving the pi electron. Now because of this configuration, or because of this resonating structure, the nucleophile is attached to the 3rd position. So you can, if you add KCN over here, then you can get pyridine N oxide with 3rd position CN group. Okay, and then if you remove oxide group, you can get pyridine 3 nitrile